I like these a lot, though. So remember Gauss's law, the whole point behind Gauss's law is that the flux through any closed surface, no matter what your closed surface looks like, as long as it's what we call a simple closed surface, then the total flux that passes through that surface where we consider flowing out positive and flowing in negative, the sum of all those is equal to the charge that lives inside there divided by epsilon naught. Flux is also flux through a little surface. It's technically double integral of E dot ds, but for a constant surface, like a flat surface, where the area is not changing, the angle is not changing, and a constant electric field, in the most basic case, flux is the magnitude of the constant electric field times the area. Okay, so in this question, we're asked for the flux through the top side. So we've got some charge sitting in the center of the cube, and we're asked to calculate the flux from that one charge through 4 of these different sides. We could use this version of Gauss's law. This one would not apply. We can't use that one because I've got some charge sitting here. That puts off an electric field that goes at angles away from the charge. So through that top surface there, that electric field is not just coming perpendicularly through it. Oh, I should put here, even in that most basic case, we do need a cosine of phi here. That electric field is not flowing perpendicularly straight up through there. It's not even flowing at a constant angle, where it's always at some angle 30 degrees or whatever. No, it's kind of all over the place. We've got some electric force vectors or field vectors pointing out this way, some pointing out this way. Right in the middle, it would go straight up. It would be perpendicular, but not over here, not over here. So we could actually do the integral. I could calculate the magnitude of E everywhere on this top surface, find what angle that electric field vector is making with my normal vector, parameterize my surface. I could do this really, really hard double integral. It's a surface integral, and it would be terrible. It would be nasty. Like, I don't even think I would do that to you in a Calc 3 problem, maybe, but it would be a really hard problem. So we're not just using this. This won't work here because this angle is not constant. E's not even constant. We don't have constant magnitude everywhere there. No, what we're going to do on this problem is think about, well, if I've got a charge at the center of the cube, I know what the total flux is. The total flux through the entire cube is just the charge enclosed over epsilon naught. So that's the total flux through all 6 sides. But all 6 sides are equivalent as far as that charge is concerned. So each side gets 1/6 of that. if you notice here, I'm not going to show you the answers because then you just type them in. Because of the symmetry of the problem, and only because of that, and because the charge is sitting at the center, each side gets 1/6 of the total. Here, we do have a constant electric field. We have constant angles. The electric field is, for this backside here, it's going perpendicularly through the surface. So that backside, the one that's like, I am not a very good artist. So I got my electric field here. It's flowing through this side here. So my normal vector points out. There's my normal vector. E is parallel with the normal vector. B here, when we have that cosine of phi, phi is the angle between these two. Technically, we say parallel here, but these are really anti-parallel. They're in opposite directions. So here phi is 180 degrees. Cosine of 180 is -1. So the flux that flows through this side, it's negative because we're flowing in. Flux flowing out is positive. Flowing into a closed surface is negative. Then the flux that flows through that surface is magnitude of E, because that's constant, times the area, because we have a constant area, cosine of 180 degrees. That's just going to be negative EA. What about this other side over here? It's the exact same scenario, only all that flux is flowing out. Everything that flowed into this side is flowing back out of that side. So this will be the same number, but positive. What about the top, the side up here? So I've got my electric field flowing parallel to this surface. It's flowing right along the surface. It's not passing through it at all. My normal vector points perpendicular to the surface. E is perpendicular to the normal vector. It's parallel to the surface. The cosine of 90 degrees is 0. There's no flux passing through the top of this cube. Same on this bottom, this side down here. The flux isn't flowing through the bottom. Same with this front, this one right here, the one that's facing us. The electric field just brushes along that surface. It doesn't pass perpendicularly through it. Through 4 of these sides, the flux is 0. This flux is negative, this flux is positive, and exactly equal and opposite. The total flux is 0. Why is the total flux 0? Because the total flux through a surface is the charge that lives inside the closed surface over epsilon naught. We don't have any charge inside. The total flux is 0, even though the individual ones are not. They just add up to 0. This is a different question. Here we want the total flux. And we kind of already answered that one. And same thing. We've got a charge inside something. It doesn't even matter where it lives inside. The total flux through the surface, Q enclosed over epsilon naught. You're done. This question, now we don't have a closed surface here. We just got a piece of paper. So this is only true right here for closed orientable surfaces. Here I've got some piece of paper. So this is supposed to be a piece of paper lying flat on the ground. And the electric field is coming up at some angle. I think they said 30 degrees. So here's E. And they give you this angle right here. It might not have been in the problem, but I'm going to say, what if that was 30 degrees? This is a trick question. They gave us the wrong angle. We want the angle between E and the normal vector. My normal vector would point up like this, so that this is a right angle. I want this angle. They do it on purpose. They give us this angle to see if we're paying attention. If that's 30, the angle I want is 60. And the total flux is magnitude of E times the area times the cosine of the angle between E and the normal vector. This angle here we call theta, by the way. This is phi. Okay, so just be careful on that one. Okay, the rest of these I think are pretty easy. Okay, let's do some couple of Gauss's law problems. So let's find the electric field of a point charge. So I know you're literally watching the lecture videos on the same thing. You just watched this. I'm just going to do a few of them in the same video. Okay, so I've got some point charge Q, and we could place that at the origin. I want to find E at some distance R. So my goal is to find E of R, where R is some distance away from the origin. So I draw a Gaussian surface that exploits the symmetry I have. A point charge sitting at the origin only has one kind of symmetry, and that's spherical symmetry. So I draw in a sphere of radius R, and I label that. And I'll even say here, my Gaussian surface is a sphere of radius R. Okay, then I got to make a couple of arguments here. I have to note that the electric field points away from positive charges. We know that. We know that from Coulomb's law. And in fact, we know Coulomb's law because we're about to derive it. But we know the electric field points away from positive charges. So let's draw that in. So that's E. And that points out. Now let's look at our sphere here. I'll draw this in red. See, this is the kind of stuff I want you to write up in a complete solution. So let's find on the sphere one of my normal vectors, maybe right there. There's a normal vector. Here's a normal vector pointing perpendicularly to the surface and pointing out. So we could see here, N also points out at every point on the sphere. On that surface, that Gaussian surface, E is parallel with the normal vector. That's all. You're either going to be parallel or perpendicular on all your surfaces. If you're not, Gauss's law was not your friend. Okay. Also, we want to note here, by symmetry, just by like the universe wouldn't make any sense otherwise. E in magnitude, the magnitude of the electric field must be constant on that surface. The universe doesn't know where I put my X, Y, and Z axes. My entire universe is a point charge that I put at the origin. It wouldn't make any sense whatsoever if the electric field were stronger down here than it was up here. Because all I'd have to do is rotate my axes and call this the Z axis. Now all of a sudden, that stronger moved, like that wouldn't make any sense whatsoever. Rotating my axes or my choice of axes should have no effect on the electric field that's produced. So just by a symmetry argument, all along the surface, all these points are the same distance away from that charge. The electric field's got to be constant all along that surface. Okay, now Gauss's law says that the flux through that surface is both the double integral of E dot ds, and that's also the same thing as Q enclosed over epsilon naught. Okay, two things happen here. That's why I have to write these out. Like this is a required step. Because E is parallel to the normal vector, because E passes perpendicularly through the surface, the dot product of perpendicular vectors is just the product of their magnitudes. So this just becomes magnitude of E ds. Sometimes we'll put dA, sometimes ds. Like I'm going to leave that in here because those literally mean the same thing. ds and dA, same thing. That's because dot product of parallel vectors is the product of the magnitudes. So I was able to do that because of this line right here. Now, because of this line, because E is constant, I can pull that E out of that double integral. I'm just pulling a constant out of an integral. And that's going to happen every single time on all of these Gauss's law problems. Then what's this? What's the double integral of dA? That's surface area. That's the definition of surface area of whatever my Gaussian surface is. Mine was a sphere. The surface area of a sphere is 4/3 pi r squared. I lied. I knew as I was writing it. Surface area of a sphere is 4 pi r squared. And that's supposed to equal my charge enclosed. My charge enclosed was just Q over epsilon naught. So that implies the E just divide over by the 4 pi r squared. And then we earlier called, this was like 2 weeks ago, 1 over 4 pi r squared. We called K, so we could call this KQ. Oh, no. 1 over 4 pi epsilon naught. KQ over r squared. That's Coulomb's law. And that's where it comes from. We've literally just proven Coulomb's law. Okay, so that's a complete write-up there. Let's do another one. Let's do a line of charge. Of charge density, sigma. No, let's go lambda. So I've got some infinite line of charge here. And it has charge density, some linear charge density here that's in coulombs per meter. So every meter, this has lambda coulombs of charge on it. I want to find E, the electric field, a distance r away. So I need to exploit the symmetry. I'm going to draw my Gaussian surface that has the same kind of symmetry as a line. The only 3D shape that has that symmetry is a cylinder. So my Gaussian surface will be a cylinder. Okay, so that's going to have some radius of r. There's my r away. And then it needs to have some length. And I need to put that on there. I have to, my complete solution includes well-labeled diagrams. So I'm going to give this thing a length of L. Now, my final answer can only depend on R. Like the question says, find the electric field a distance R away. It shouldn't depend on how big I make this cylinder up and down. It can't depend on L. I made up L. My answer will depend on R because, I mean, obviously, the further away you get from this line, the smaller the field will be. But it won't depend on L. L better cancel out, and it will. Okay, now I have three different surfaces here. I've got, let's call this number 1 up here, surface 1, surface 2, and then think of this as a soup can, the label of the soup can, surface 3. I have to find the flux through each of those surfaces. So the first thing I want to note, I've got this line of charge. Just think of these like a bunch of little positive charges here. That's all they are. It's just a bunch of little protons. The electric field has to point away from there. It has to. So my electric field here on the surface has to point away, radially out, away from that line. So let's write that down. E points away from the line. Where's my normal vectors? So I'll do the normal vectors here in green. On the label of the soup can, like right here, it would say Campbell's soup. Here out on the label, the normal vectors point the same direction I just said, perpendicular to the surface. Same way I just pointed all those E vectors. That's a little right angle I'm drawing there. On the top and bottom of the can, normal vectors will point here, it'll point up, down here, it'll point down. So on, like you can clearly see here, E is pointing side to side, normal vectors pointing up here. So on surface number 1, the top up there, E is perpendicular to the normal vector. It's an arrow. The dot product of perpendicular vectors is 0. The flux up there, flux number 1 is 0. Because none of the electric field is flowing up. It's not flowing through the top or the bottom. Same thing too, on 2, down here on the bottom. On surface 2, the bottom, E is still perpendicular to the normal vector, flux 2 equals 0. This is, I need you to show all this on your solution on 3. That's the label. That's we had E pointing this way. We had the normal vector pointing this way. E is parallel to the normal vector. Always, every place on the surface. So the double integral, the flux through that surface, So let's call this flux 3 of E dot ds. Right. Remember, I'm making ds a vector here because the vector ds is the normal vector times just the differential ds. Because they're parallel, I can drop that dot product and make these magnitudes. The magnitude of the normal vector is 1, so we just get our ds. Because E is constant on the surface, see, I said that right here. I haven't said that yet. I need to say that. So let's make a note here. E is constant in magnitude on surface number 3. It has to be. It wouldn't make any sense mathematically for the electric field to be bigger up here than it is down here. Because this is an infinite line. This goes on forever. What's special about here versus here? Now, it might be bigger closer in. And sure it is. It's probably bigger closer in, but I'm always the same distance away. If I'm on surface 3 here, I'm always the same distance away. The electric field could only possibly depend on distance. So if I'm at the same distance, I got to have the same strength of field. It might point in a different direction, but it'll have the same magnitude. So because of that, I can pull this E out. Okay, so that magnitude of E times the integral of ds, that's just surface area. Surface area of the label, not the entire cylinder. Remember, we're not counting the top or bottom, just the label. Well, we could imagine unrolling that label. This was R here. Then if we unroll this and turn it into a rectangle, it would have this length, which is 2 pi r, and that height that we called L. So this will be magnitude of E, 2 pi r L. Okay, that's half of what we need. Recall Gauss's law says the double integral of E dot ds, the flux, is the charge enclosed over epsilon naught. How do we find charge enclosed? Charge enclosed, I'm going to say this over and over again. Charge enclosed is always some form of volume enclosed times some form of density. In these infinite cases, we don't have a finite amount of charge. We have an infinite amount of charge total. So when I say volume, I mean generalized volume. That volume might be a length, it might be an area, it might literally be volume. That's always going to depend on what kind of density we're given. See, up here, our density was coulombs per meter. What do I have to multiply that by to get coulombs? That's charge per unit length. So if I multiply that by a length, I get charge. So my volume enclosed here is just a length. See, let's redraw our original scenario. I had this line of charge here. Here was my Gaussian surface. With some distance r away. This was a length L. How much charge did I actually capture? What is the charge that lives inside there? It's only this charge right here. That's what's enclosed. So when I say volume enclosed, I mean whatever version of volume times my density will give me charge. Remember, we had this guy here that was measured in coulombs per meter. I need to multiply him by this length, L, that's the length of it. That's going to be meters times coulombs per meter. Meters cancel, and I get coulombs. So my Q enclosed here is L times lambda. All right, so now we put all this together. The flux through the surface is the double integral of E dot ds, which is Q enclosed over epsilon naught. Over here, it's right here. I get magnitude of E times 2 pi r L. That's supposed to equal L lambda over epsilon naught. The L's cancel. If the L's didn't cancel, I've done goofed. And I get dividing over. That's what we're trying to solve for, is E. Lambda over 2 pi r epsilon naught. So there's my magnitude, and then my direction is it points radially out from the line. So the electric field of a line of charge drops off like 1 over r. Okay, one more. Next time we'll do the cylinder of charge, which is what your group assignment is. I'm going to do it for you. Let's do a plane of charge. With charge density sigma, and this will be in coulombs per square meter. So it's a charge density per unit area. So I've got some infinite plane of charge. That is a terrible drawing. Let me try that again. I'm just not very good with this pad. Okay, so this is supposed to be a plane. It extends forever that way and like that. This is a plane of charge. And if I were to cut out a little area in here, the amount of charge that would live there would be that charge density times the area. That's what we mean by volume enclosed here. My volume enclosed will be an area here. Okay, so we pick a Gaussian surface that has the same kind of symmetry as this plane. You could do a pillbox. I think in the other video I did a pillbox. I'm going to do it with a cylinder here. So my Gaussian surface will be a cylinder that goes above and below the plane. Needs to be symmetric, has to have the same kind of symmetry that the plane does. And here's my intersection right there. Maybe I'll make that one red. That's my intersection of the plane and my cylinder. Okay. I'm going to have a radius r. Cylinders have 2 dimensions, radius r, and we'll say it sticks up a distance L above the plane here. So the total length would be 2L. I could do it either way. I could call L the total length, but you'll see it won't matter here in a second. But I gotta label my dimensions. I need a well-labeled picture. Okay, again, just like the last problem, I've got 3 separate surfaces, and I need to find the flux through both. So I've got surface 1 up here, surface 2 down here, and then the soup can label again, surface 3. The electric field of a plane has to point away from the plane. It wouldn't make any sense for it to point at some angle to the plane. Like, what angle would it be? That wouldn't make any sense because the plane goes on and on forever. The electric field has to point away. So I'm going to draw a bunch of E's here. Maybe I shouldn't do blue since I already used blue for the diagram. Pink. So these are all E. Let's draw some here on the surface. Down here, the electric field will still point away, but now that's down because away is down. All right, so let's make that note. Note number 1. E as a vector points away from the plane. Perpendicular to the plane. Also, up here at a height r, like up here on this top surface, E must be constant in magnitude because all these points up here are all the same distance away, this distance L away. So up here, let's look at surface 1 first. In magnitude, the electric field must be constant on surface 1, up here on this circle. Because they're all those points are all the same distance away. And E is parallel with the normal vector. My normal vector, let's draw some of those in. The normal vector has to point up. Okay, what about on surface 2? Well, that's the exact same scenario, right? So I could just say here, same on 2. What about on surface 3? My normal vector points out away from the surface. E points up here. E is pointing up. Those two are perpendicular. E is perpendicular to the normal vector. That flux is 0. When we do E dot ds, the dot product of perpendicular vectors is 0. That flux is 0. So we could even write that here. We could say here, flux 3 equals 0. So the only flux I'm going to have are through the ends of the can here. Okay. So the double integral of E dot ds. Let's look at just number 1. Because they're parallel, because of this, I can write that as magnitude of E ds. Because E is constant on surface 1, I can pull E out. Okay, what's double integral ds? That's just the area of surface 1. Surface 1 is this circle right here, that disk. That's just pi r squared. Well, same for 2. Surface 2 is the same thing. That flux will be another magnitude E pi r squared. And then surface 3, I mean, I know I already wrote it, but I'm going to write it again here. Surface 3, that flux was 0. So then the total over the entire Gaussian surface would just be that plus that, 2 pi r squared magnitude of E. Okay, what about the other side of Gauss's law? Q enclosed. Q enclosed is always going to be some, I'm going to put it in quotes here, some form of volume enclosed times my density. And by volume enclosed, whatever kind of length area, volume I need so that when I multiply it times this guy, I get coulombs. So I need to multiply by meter squared, that's an area. My charge enclosed lives right here. That's it. That's all the charge that lives inside this blue cylinder. It's that disk, it's an area. So volume enclosed here in this case is just area enclosed times my density sigma. Well, that area, that's just going to be pi r squared. So now I put these two together, double integral E dot ds equals Q enclosed over epsilon naught. Don't forget your epsilon naught. I have a habit of leaving that off myself. There's the left side. Here's the right side. Q enclosed pi r squared sigma over epsilon naught. Oh, look, the r squareds cancel. The pi's even cancel. Divide the 2 over and you get magnitude of E equals sigma over 2 epsilon naught. That is the electric field of a plane of charge. It's constant everywhere in the universe. The direction changes. Like on one side of the plane, it goes to the left. On the other side, it goes to the right. It always points away from the plane, but it's constant in magnitude. Okay, so what if we had 2 planes of charge? Let's say we've got some positive sigma here and some negative here. This guy here is creating an electric field that's constant everywhere in space, everywhere in the universe. The electric field will point away from here. And I'm going to draw these all the same because they're all the same magnitude. Doesn't matter if you're 1 billion miles away from the plane or right up close to it. You get the same strength of the electric field. This guy, he's a negative charge, same idea, only now the electric field will point toward him. And that's the same everywhere in space. Well, in these regions out here, all these positives, all these negatives, or all these towards and aways, these all cancel out. I get E equals 0. Same over here, E equals 0. Inside, I get E equals twice, just one charge. So in this region here, the magnitude of E is sigma over epsilon naught, twice that answer. This is what we call a parallel plate capacitor, where the sigma here is the charge density on the positive plate. Now, in the real world, we can't have infinite planes of charge, but what we can have are like square plates that are really close together. So we might have some positive Q here, some negative Q here, and sigma is just charge per unit area, the charge on the positive plate divided by the area. And as long as this distance here is small compared to those areas, the electric field is approximately this. And we could just fill that in here. Q over A epsilon naught. Inside here, we get nearly a constant electric field. Now, towards the edges, we get what's called edge effect, and the electric field kind of bows out. But that is so small that in the real world, we just ignore it. And this is what's called a parallel plate capacitor. We're going to talk about capacitors in the coming weeks, and here's our first look at one. What's cool about these, though, is that the electric field is constant in here. So if you have a constant electric field and you put another charge in there, say I put a proton in here, it will feel a constant force. Remember, electric force is just electric field times charge. If we have constant forces, we can use the constant kinematic equations from physics 1. F equals ma, x equals x naught plus v naught t plus 1/2 at squared, all your projectile motion kind of equations. All those will apply here because we have a constant force. So we got a good couple of questions coming up, some good written assignments based on a capacitor here. Okay, I will do the cylinder of charge, like the more advanced version of this one, again next time. And that's a good place to stop.